Good afternoon. My name is Tom Sawinski, and I work in the Department of Energy's Office of Advanced Reactor Technologies. I'm here today to present to you an exciting mission-supporting opportunity in the field of reactor concepts, development, and demonstration. Before we begin, I'd like to go over the general mission and objectives of both the Office of Nuclear Energy and the Office of Nuclear Reactor Technologies. One of the main focuses is to develop technologies and other solutions to improve the reliability and sustain the safety and extend the current life of our current reactor fleet. Another major field involves developing improvements in the affordability and advancement of new reactor designs. That is what the majority of this mission supporting item will be addressing. Two other major fields involve the development of sustainable fuel cycles and also to develop capabilities to reduce the risk of nuclear proliferation as well. The Office of Nuclear Reactor Technologies supports the mission of the Office of Nuclear Energy by focusing on keeping the current fleet operating safely and developing new reactor technologies. The ways this is done is to promote technologies that have great promise to enable new nuclear power, to conduct research and development to maintain safe operation of the existing fleet, to honor commitments to other federal agencies and international partners, maintain our unique facilities and capabilities to support both government policy and industry needs, and, as this last bullet point shows, to explore new high-risk and high-reward technologies, which is a major objective of this current mission-supporting opportunity. The next bullet gives a brief breakdown of the Office of Nuclear Reactor Technologies. NE-72 deals with light water reactor technologies and reactor sustainability. NE-74 deals with advanced reactor technologies, which is what the majority of this presentation will be dealing with. And finally, NE-75 deals with space and defense power systems. All these activities are designed to address technical cost, safety, and security issues with various reactor concepts. This diagram just provides an overview of what I previously stated. The main focus that I'd like you to draw your attention to is to the Advanced Reactor Technologies field. Under that, we have the Office of Advanced Reactor Concepts, where we are showing our current work in the area of fast reactors, high temperature reactors, or HTRs, and advanced small modular reactors, which are small modular reactors utilizing non-light water capabilities. So in the area of advanced reactor technologies, we want to address several questions in our research and development. First off, we're looking to improve the affordability of nuclear power. This will be very important for its sustainability and for its advancement into the future. We also want to improve inherent safety of advanced nuclear reactors. This is important, looking at different safety systems to ensure that the future of nuclear power will be beneficial both to the industry and the public and safe. Related to safety is we want to promote non-proliferation. We look at advanced reactors and how that can aid us in that particular endeavor. And related to that is nuclear waste and the minimization of nuclear waste by utilizing advanced fuel technologies. Also looking at the economic side of things, you want to see how we can expand into non-traditional nuclear energy markets. How can we use other features of reactors besides just baseload generation? Another important field is how can we increase the performance and efficiency through new materials and advanced systems or components. Materials and systems are very important for the development of any reactor design and is a large focus of our office. So a first field of reactors that is being currently looked at by the Office of Advanced Reactor Concepts are fast reactors. We have main fields that we are currently looking into. First field is concept development and technology maturation. We look to assess these assessments to guide our innovative research and development. And one such example that we've presented, and there's a small graphic of that on the top of the slide, is the conduct of small-scale sodium fast reactor component testings at the Materials Engineering Testing Laboratory at Argonne. This is a very innovative system and allows us to not only look at material aspects of future reactor designs, but also to look at a comprehensive system performance within these environments of liquid metals. Related is advanced materials. As I stated in the previous slide, this is important for a majority of high-temperature reactors and for fast reactors as well. In 2012, we looked at candidate alloy selections and down-selected to 2 main alloys. As we see, intermediate testing is now taking place of these 2 alloys. Also related, we want to make sure that these new reactor designs will be safe. There are currently international validation studies going on, and we're also looking at licensing aspects to look at the future of actually implementing and developing these reactors in the United States. Also, when you have these reactors, we have to be able to inspect them and make sure that while they were running, they're meeting all their criteria. Another field that is helping with that is ultrasonic viewing technology. This is work for under-sodium inspection, which is an opaque environment that allows us to do in-service inspection of various materials and components in a reactor, which is very important to actually see these reactors up and running. And there's also international collaboration on that particular field. Another field for advanced reactor concepts is the high-temperature gas-cooled reactor area. This was formerly under the Next Generation Nuclear Plant, or NGNP program, to produce both electricity and high-temperature process heat for other applications. Some work that was done under this program involved collaborations with the Nuclear Regulatory Commission to establish a licensing framework for these particular reactors. And going down that path is actually beneficial for establishing a licensing basis for future reactor designs as well. So that was very beneficial work. And also partnering with industry as well. It's important to get buy-in from those that may be potential in the future to actually run these particular reactors. And also collaborating with national laboratories and universities and as well with the international community to perform the research and development necessary to reduce the overall technical risk by getting many key players into the development of reactor designs. Some of the ongoing R&D focus areas in high-temperature gas reactors is the fuel qualification, materials once again, design and safety methods, and licensing support. So those are all major areas that will be beneficial for the future of nuclear reactors. Another reactor design is the fluoride high-temperature reactor. That is utilizing a fluoride salt-type coolant, and a majority of that work has been done very closely with the NEUP program through an integrated research program. There's also ongoing work looking at different materials inside these loops at Oak Ridge National Laboratory. So as you can see, they're working on hydraulic performance, materials, and key components as well. Also, we have international collaborations, which has been very beneficial for this particular design, both with China and the Czech Republic. And also, a major portion of the advanced reactor programs is advanced small modular reactors. This plays both into the economics and safety features of the new reactors as well. Some main things that are currently being worked on in the advanced small modular reactor field are instrumentation controls and human-machine interface. Such items are advanced high-temperature instrumentation, going back to being able to do in-service inspections, and also other in-service inspection technologies and techniques. Another field is component and technology development, working with advanced reactor technologies to emphasize operations of these particular reactors, new compact configurations to save on size and cost, and new and innovative energy conversion systems to maximize the heat and other energy that is being produced by these particular reactors. And once again, advanced materials. And as you see, which ties into several other reactor areas as well, safety and licensing will be important for the future of these reactor designs. And under that, we have advanced modeling and simulation, seismic isolation, seismic modeling, all very important items to be considered when looking at future licensing of these reactor types. So now I'd like to get into the actual details of the mission supporting concept that we are discussing at today's presentation. I wanted to highlight to you that this particular mission supporting field is looking for revolutionary improvements to reactor performance and/or safety. This is a very innovative opportunity and allows for the next round of research and development for future reactor designs. First off, major areas that we're looking at are incorporation of advanced systems or components into existing concepts. Some examples are Generation 4 systems for the gas-fast reactor, molten salt, lead reactors. So looking at next phases for particular components for these new systems. Next is looking for inclusion of innovative design alternatives. This can range from a wide variety, from brand new fuel types to nano-engineered coolants and other items in that particular category. And this third bullet shows we're looking even for reactor designs employing radically different technology options with advanced coolants, fuel, or even different operational regimes. And finally, there's looking at small modular reactors with unique capabilities to address different operational missions other than baseload electric power, such as process heat or mobile reactors that can be used during emergency situations. As you can see, there's a large chance to think outside the box in this particular mission supporting field. And what we're mainly looking for is the overall technical merit of this particular ideas and thoughts to set the framework for future program supporting areas. This just gives an overview of some of the items that I've addressed previously in the previous slide. A variety of technologies are being pursued, such as the high-temperature gas reactor and sodium-cooled reactors. There were liquid salt reactors work via the 2011 IRP and the 2014 IRP with the fluoride salt high-temperature reactors. And different technologies have actually been reviewed by a panel, the Technical Review Panel, in collaboration with industry. And more on that can be found at the website addressed in this presentation. So once again, this bottom portion reiterates that the scope includes major innovations to reactor areas that we've already discussed, and also radically different new technology options. So literally this offers you a good chance to think outside the box. So finally, I'd just like to go through some recent awards to give you an idea of some of the areas that have been worked on in this field. So in 2013, there was a feasibility study of a pedal bed cool reactor compared with the benefits of current light water reactors, and also work on tritium mitigation and control systems for fluoride salt high-temperature reactors. 2012, some examples were fuel and core designs for heavy metal loading limit and to improve safety of liquid salt-cooled reactors, stationary liquid fuel fast reactor concept for transuranic uranium burning, and in fiscal year 2011, there was feasibility and safety assessments for various advanced reactor concepts through the use of vented fuel. So as you can see, this area offers you a wide variety of choices to look at. And with that, I will open it up to questions.
What are two candidate alloys for advanced materials?
I believe the ones we are currently looking at are, one is 709 alloy, and the other is, I believe, grade 92 steel are the two that we are currently down selected in that particular field.
Are supercritical water reactors considered?
In this particular case, I think the only thing that we're not considering is actual standard non-light water reactor design. So supercritical does fall in an advanced category.
What about a different design LWR?
Light water reactors are...
For example, a small modular reactor LWR.
No, that's separate. When I referred to advanced small modular reactors, that is only referring to non-light water reactor concepts. So there's a separate area for light water reactors.